Yeah, next let us see about charge distribution in case of a conducting plate. So, it means that concept is about, first let us see the charge distribution on charge distribution on large conducting plates. So, in that first case we are taking like charge distribution on isolated plates. A charged isolated plate. That means only one plate we are taking here. So, that means now this is the plate I am taking here, and a charge Q is given to this plate here. So, now we need to discuss how that charge will be distributed on that surface. So, we derived an electric field when we were discussing about electric field due to the infinitely charged plane. There we mentioned for plane it is sigma by 2 epsilon naught, and if it is a conducting plate, then we need to write that resultant field as sigma by epsilon naught we need to write. That means we need to multiply that with the 2, that plane of charge with the 2, because we mentioned that the charge given to the plate will distribute on both sides of the plate here. So, now let us see how the charge distribution is charge is distributed. Suppose to that plate we are giving a charge Q. So, that means let us assume here, let Q be the charge distributed charge given to the plate. So, we are assuming that, so our assumption is let Q be the charge given to the plate, right? Charge given to the plate. And now suppose this side I am assuming that some Q is present on this side, and this side I am assuming it as Q minus Q. The remaining charge will be there because it is isolated plate, and so total charge on that must be same. And so next we are assuming that, so let Q and Q minus Q be the charges on left and right surfaces as shown. So, we are assuming that. So, we are assuming that Q is the charge present on the left side and minus Q is the charge present on that right side. So, right. That means what actually we are assuming is, I will draw this diagram again here. So, this is our assumption what we are taking here. So, this charge, some charge Q will be distributed on this. So, this is Q, and this side again some charge will be there on this side also. And so, this charge we are assuming it as Q minus Q. So, right. So, now simply what to find that Q value, small q value, what we should do is, so we should take a point here. So, I am taking a point P. So, now let us write electric field at that point there. So, let P be a point inside plate. So, now the resultant electric field at that point. So, the electric field due to this charge will be along this direction away from this, let it be E1, and electric field due to this will be E2 will be there along this direction. So, right, and let us suppose A be the area of this plane here. So, then I can write this as E1 minus E2 because they are in opposite direction, and this value should be equal to 0, right, because the point P is inside the conductor. Inside the conductor electric field should be equal to 0. And so, now I can write this as this E1 means Q by A by 2 epsilon naught. That means it is nothing but sigma by 2 epsilon naught minus capital Q minus Q by A by 2 epsilon naught. So this value should be equal to 0. Got it? Sigma by 2 epsilon naught we are writing, because this you can treat as one plane, infinite plane, and this is another plane. So the charge density on this will be sigma by A, where A is the area of this plane, and similarly this is sigma q minus q by A, and similarly this will be q minus q by A, that gives the sigma value. And so then that A and epsilon naught you can cancel there. So I can write this as q minus q plus q is equal to 0, or I can write this as q is equal to q by 2. And so from this what we can conclude is, therefore charge will be distributed equally on either side. Charge will be distributed equally on both sides, right? So that is the case when you are giving some charge to a isolated metal plate. So that means now when you are giving the charge, whatever the charge you are giving, the charge will be distributed equally. For example, if you are giving minus q, so minus q by 2 will be on one side and plus q by 2 will be on the other side. If you are giving plus, for example, 2q charge, so q will be on one side and a q will be another q will be on the other side. So charge will distribute equally like this. So that is in case of isolated plates. A single plate if you are taking, right? Now the second case what I am taking is, let us suppose this is a neutral plate. A neutral conducting plate is placed in the external field. So let us see what will happen there. So now case 2. When a uncharged conducting plate is placed in uniform electric field. So now suppose say this is a conducting plate here, uniform electric field, suppose say E, we are taking it as E, right? And so now that is uniform electric field, E will be there. And so throughout this region that electric field will be there here, right? And so we know, we discussed already in the properties of conductors, like when an external, that means when a conductor is placed in external field, the charges will be induced on the surface of this conductor such that the electric field inside the conductor will become 0, right? And so now here the charge distribution will take place like this. And so now suppose this electric field is there along this direction, for example. And so all the electrons present on this inside this conductor will experience a force this side. So free electrons will experience a force this side, and so that some negative charge will appear on this conductor here. So right, got it? All the electrons, electric field is along this direction, so the negative charges will experience a force in opposite direction. And so negative charge will appear here and an equal amount of positive charge will appear here. So these are induced charges. So both of them are induced charge. Let's suppose I am assuming that magnitude has some q. We need to find that q value here. And so these electric field lines will end here normally on this. And they will start from this opposite point here. So like this, the electric field distribution will be like this. And now here we are neglecting the end effects there. Those are called fringing effects. We are neglecting such end effects. And that means the field at the like at the end is not like this. Some lines may enter, that means here perpendicular means you will get like this. Such a deviations may be there. We are not taking like this. We are taking well inside this conducting plane here. And so now again let us take a point P here. So now if I take the point P, then here two fields are there. So one is external electric field will be there like this. This is the external electric field, and the induced electric field will be there like this. And so their resultant field resultant must be equal to 0. So at any point P inside conductor, resultant field is 0. Therefore, electric field at that point we can write as the resultant of external field plus induced. So that we need to write here, and this value should be equal to 0. So if I write the magnitude, then I can write this as, so E minus, this we can write as, suppose I am taking that Q is a charge present on that, so Q by A. So this will be like minus Q by A, Q by that means sigma by 2 epsilon naught, and this is also due to this charge also sigma by 2 epsilon naught you will get. So that sigma by 2 epsilon naught plus sigma by 2 epsilon naught will be sigma by epsilon naught. That is what I am going to write here. Got it? That means again while we are writing, what I am saying is, while we are writing the charge electric field due to this induced charge, negative charge and positive charge, the resultant field we need to write. Due to this negative charge when you are writing, you can take that as one infinite plane. So it is sigma by 2 epsilon naught we can write. That will be towards left. And due to this induced positive charge will be towards left only. And that is also given by sigma by 2 epsilon naught. And as we are, this is as induced charge, these sigmas must be same. The magnitude of the charge induced must be same, so that the net charge is 0. And that charge I am taking as Q. So Q by A by epsilon naught. So this is equal to 0, right? And therefore I can write this as Q is equal to, or Q by A, sigma is equal to, what we can write it as epsilon naught into E. And if you want to particularly write this charge, then epsilon naught E into A we need to write here. So this is a charge density, surface charge density, and if you want to write charge, then we can write as sigma into epsilon naught into A. So that will be the surface charge density there, right? So that will be the induced charge. So this is the induced charge appearing on this. So this is the induced charge appearing on the surface here. So the amount of induced charge is given like this, right? Now let us take one more extension here. Extension in the sense, suppose I am taking that a charged conducting plane. So that means now I am taking it as a third case here. So case 3, when a charged conducting plate is placed in external field, the same thing. That means I am assuming that already some charge Q is given to this plate here. So that means Q is the charge given to this plate here already. This is the initial charge. So the initial charge given to the plate is Q we are assuming. Now additionally some induced charges will be there. So then that means here this side I am assuming this net charges. We know out of this Q by 2 and Q by 2 will be induced on this. And so now final charge we need to write here. Final charges on each side we need to write here. So that means now this side I am taking it as this side the charge is Q by 2 plus Q, small q, and this will be, that means minus Q that side. So that means this side I am taking as charge Q1 and this side is Q2, let us take, right? Where that Q1 I can write it as, so first let us write Q1 and Q2. I am assuming this net charge on this is Q1 induced plus this given charge, that resultant we are taking there. And this side we are taking as Q1 and this side we are taking as Q2, right? And so now this we can write it as, so now this again same. At any point P inside conductor, resultant field is 0. Resultant field is 0. Therefore, I can write this as external plus field due to the net charge. That means that Q we can write here. Whatever this Q1 and Q2 we can consider here. Right? So, this value must be equal to 0. And so, now here this value now and again here we can't conclude whether it is positive charge or negative charge here, right? That actually depends on this field and this value here. The how much we are applying field and how much charge is given to that. So that will depend on that whether it is finally we are getting this positive charge or negative charge. So that I am assuming that as positive charge here. So right, I am assuming this side also that resultant charge I am assuming it as some positive charge only I am assuming here. So sign we will get now. So this side some Q1 charge is there and this side some Q2 charge is there we are assuming, right. And so now this is the resultant field at this point is E. Now due to this, so this directions also we should drop here. So just I am taking the point P here. This external field will be there along this direction, and due to this Q1 it will be along this direction, and due to this Q2 it will be along this direction. So then Q1 is in the same direction of external field. So I am writing that as plus Q1 by A by 2 epsilon naught, right, minus Q2 by A 2 epsilon naught. So this value should be equal to 0, right. And so now, therefore I can write this as finally E plus Q1 by 2A epsilon naught minus Q2 by 2A epsilon naught is equal to 0, right. And so now we need to write this Q1 and Q2 relation here. The Q1 and Q2 relation means whatever the charge given to this, that charge will be distributed equally on this, and then this Q1 we can write it as Q by 2 plus some induced charge Q, and this charge we can write as Q by 2, that means this side you can write as Q by 2 minus Q, and this side you can write it as Q by 2 plus Q, right. But this Q1 is equal to, I can take it as, but small Q1 is equal to, so I can write this as Q by 2 minus Q, and this value will be Q by 2 plus Q. So then you can substitute in that equation there, therefore I can write this as E plus Q by, that means Q minus 2Q by 4A epsilon naught minus Q by 2, sorry, Q plus 2Q by 4A epsilon naught. So this value is equal to 0. Now we can simplify and find this Q and small q values. So that small q values I can write this as this 4A epsilon naught term will be cancelled. So E is equal to, this term we can write it as Q by A epsilon naught you will get. Q by A epsilon naught, and that implies this Q value will be E into A into epsilon naught, that means same as that of our previous value. Additionally, we need to add that this Q by 2 and Q by 2. Therefore, the charge on the left side will be equal to, the left side charge will be equal to, I can write this as Q by 2 minus E into A into epsilon naught. So that is what I said there. The finally whether it is positive or negative, that depends on this magnitude here. So if this E A epsilon naught is for example greater than this, then you will get the charge as negative. If the Q by 2 is more than that, then you will get the charge as resultant charge as positive only, right? And so now Q on the right side we can write it as Q by 2 plus EA epsilon naught. So that is the charge distribution taking place when you are taking an isolated charge, isolated charged plate or a neutral plate, and already some charged plate is placed in this external field. And now let us discuss about this parallel plates here. Means now parallel plates in the sense here we are taking a single isolated plates only. Now we are taking a combination of plates then. We need to consider the combination of plates. So all we assume them as conducting plates only. And actually these conducting plates we will discuss in capacitors also. But if you have an idea about these plates, then in capacitors you can solve them easily. So then let us say this. So we are discussing about parallel conducting plates. And all them are assumed to be infinite plates only when compared to the distance between them. So now for example I am taking the plates like this. This is a cross section view. That means the plates are placed like this. Their plates will be like this. Just I am representing the cross section. Here one plate will be there like this perpendicular to the board, and here one plate will be there like this. And for example I am taking this another plate here. So, right. I will take another plate also, so that conclusion, that means you can write those conclusions directly. So let us take them as identical plates and they are separated by some equal distance like d. So right, I am assuming like capital Q1, capital Q2 and a capital Q3 and a capital Q4 are the charges given to those plates there. So just mention that. Consider 4 identical large conducting plates. 4 identical large conducting plates are placed parallel to each other at separation d, at equal separation d as shown. Let Q1, capital Q1, Q2, Q3 and Q4 be the charges given to the plates respectively. Now I am assuming charges on each surface we need to find here. So that means this side I am assuming as Q1, this side it is Q2, Q3, Q4, Q5, Q6, Q7 and this is Q8. So got it? Now the small Q1, Q2, Q3 and so on Q8 are the charges appearing on the different surfaces, the different faces or different surfaces of those conducting plates there. So we need to derive an expression for these charges only now in terms of this total charges, right? So that's a very easy calculations we can write here. So that means just by observing this, what we can write is, so by the conservation of the charge, Q1 plus Q2 is equal to capital Q1. So like that, some basic relations you can write here. The sum of these two charge must be equal to Q1, sum of these two charge must be equal to Q2, like that. These are like we are assuming all are isolated from each other. That means there is no contact, direct contact between them. They are placed close to each other only. One plate is not connected to another, or no plate is connected to the ground here. That's what we are assuming. And so next similarly I can write like Q3 plus Q4 is equal to Q2, and next I can write this as Q5 plus Q6 is equal to Q3, and next I can write this as Q7 plus Q8 is equal to Q4. This equation, all these relations, let us take it as equation 1. So right, now I am taking a point A in this one of the first plate here. I am taking a plate A. So just we need to write a resultant field at that point A. So take So that means we are taking consider a point here inside this conducting plate here, inside the conducting consider a point A in the first means from the left side I am counting. So in the first conducting plate. So then now I am going to write the resultant electric field at that point there. And we know as we are taking that conducting plate as inside this conductor, that means the point we are taking as inside the conductor. So resultant field will be equal to 0, right? And so just we need to write the field due to this different charge distributions there. So I am directly writing that due to each plane sigma by 2 epsilon naught, that sigma we can write as q by a. So I am directly writing that for this q1 only the charge will be, the field will be along this direction. Remaining all the field will be along this direction here. So see this. So I am writing this as q1 by 2a epsilon naught. I am taking that q1 by 2a epsilon naught common. That will be there for each term. So I am taking the term common. So that means 1 by 2a epsilon naught q1 minus. So now see the charges. This q1 will be along this direction due to the remaining q2, q3, q4 all that will be along this direction. And so then we need to subtract them, the field direction. So q2 minus q3 minus q4 minus q5 minus q6 minus q7 minus q8. This value should be equal to 0, right? Now from this, that means all these are sigma by 2 epsilon naught. That means if you write this sigma by 2 epsilon naught, sigma by 2 epsilon naught, you will get that sigma will be different for different planes here. What I am writing, got it? That means due to this, if you want to write, this will be along this direction, q2 by 2a epsilon naught. Due to q3, if you want to write, q3 by 2a epsilon naught, that 1 by 2a epsilon naught we are taking common. And so now this term I can write as q1 is equal to q2 plus q3 plus q4 plus q5 plus q6 plus q7 plus q8. Now see I am grouping the terms here. So now by using this first equations, that means now observe this, q3 plus q4 we can write as q2. Like similarly q5 plus q6 we can write as q3. So like that we can replace them. Therefore this q1 is equal to, now this q2 value also we can replace by using this equation here. So I can write this as q1 minus small q1 plus q2 and plus q3 plus q4. Got it? These values. And therefore I am writing this term to this side. Therefore finally what we can conclude is q1 is equal to q1 plus q2 plus q3 plus q4 by 2, right? And similarly if you are taking this point here, similarly suppose I am taking another point in this rightmost plate, last plate here. So that means directly I am writing here, similarly field at a point in the rightmost plate is 0. Therefore you will get that expression as, that means EB is equal to 0. If you write this such a similar equation, that means take this point, now electric field due to this Q8 only will be towards left, and remaining all charges from Q1 to Q7 electric field will be along this direction. So you need to write such an equation. The only difference is here all the terms are positive, and only for Q8 you will get the negative term, because Q8 will be towards left. And if you simplify like this, then you will get the similar conclusion there. So similarly we can write this as Q8 is equal to Q1 plus Q2 plus Q3 plus Q4 by 2. So that means now finally what we can conclude regarding this outermost surfaces is the charges appearing on the outermost surfaces on the left or rightmost surface. That means on the outermost surfaces they are equal and the charge will be equal to half of the total charge given to the system. So this is half of the total charge given to the system. So if sum of the charge, for example, Q2 is negative, then you need to take negative sign. If Q2 is not there, for example, for second plate no charge is given, then you should take 0. So whatever the charge given to the system, so that charge we need to consider there, right? So the half of the total charge given to the system. So that is one of the important point there. So that means write that conclusion there and write this entire point in a box, or first write that and keep that point in a box. The charges appearing on outermost surfaces are equal and it is equal to half of the total charge given to the system. Half of the total charge given to the system. That is irrespective of number of plates here. 2 plates may be there or 100 plates may be there. Whatever the total charge given to the system, we need to add and we need to divide with 2 there. Half of the total charge given to the system. So keep this total sentence in a box. So that is one of the important point regarding the parallel plates there. So the charge present on the outermost surfaces will be always same. So that point is true in any combination. That means even if you are taking any extensions, one of the plate may be grounded or some plates may be connected together. So that means then charges appearing on outer surfaces will be always same. And if no such a grounding or other connections are there, then we can say that the charges appearing on them will be equal to half of the total charge given to the system. So when you know this like Q1 and Q8 values, we can write about the remaining charges easily, right? So I am rubbing this calculation here. So then you can now write the expression for Q2 and Q7. So because we know the charge on one side and we know this conservation relation, so we can write the remaining other side charges easily. Now I can write this Q2 charges. Now this Q2 value is equal to Q1 minus Q1, capital Q1 minus small q1. So which I can write as capital Q1 minus, this charge is nothing but Q1 plus Q2 minus, plus Q3 plus Q4 by 2. And therefore this we can write it as Q2 is equal to, and take LCM and simplify that. So Q1 minus Q2 minus Q3 minus Q4 by 2 we can write. So that is the charges appearing on this inner surface of this charge here, right? Or you can write it as Q by, that means Q minus sigma of Q, remaining minus of sigma of Q by 2 we can write here. That means that relation is nothing but. So Q1 minus the sigma of Q by 2 we can write here. So sigma of 2 means the charge present on the remaining plates there from second onwards. That is from 2 to n. From second plate to up to infinite plate you can write there, right? Or simply that is nothing but you can also write it as, for example, this we are getting as 10 coulombs, for example, if you are taking here. For example, here if you are getting this as 8 coulombs, then easily you can write it as remaining 2 coulombs will be there on this side. So that is nothing but this conclusion what we are getting here. So that means in numericals you can directly write like this. If 10 coulombs of charge is there and here for example 8 coulombs we are getting, then this 8 coulombs is nothing but like Q1 plus Q2 plus Q3 and so on, the average, the half of the total charge. The remaining 2 coulombs must be there on this side here. So that is nothing but what this our conclusion is. So then this is a Q2 expression there. Now similarly this Q7 you can write it as Q4 minus Q8 you can write here, and therefore it is nothing but this Q7 by substituting this Q1 plus Q2 plus Q3 plus Q4 by 2. And therefore, I can write this as this is Q4 minus Q1 minus Q2 or minus of Q2 plus Q3 by 2. That means Q4 minus of the charges on the remaining plates we need to write there. That is nothing but that relation here. So this is Q7, right? And now suppose if I want to write the charges about this Q3 and Q4 or the Q5 and Q6, then simply you can follow the same procedure, or you can also write by using our conducting shells. If you are taking like a conducting shells, then we know that we can write this as the charges appearing on the opposite faces. In case of concentric shells, we already mentioned that the charges appearing on the opposite faces will be equal and opposite, right? Because here also these are placed very close to each other. So then here these two charges must be equal and opposite. So that if you want, you can prove again. Suppose I am taking a point C in this, then again write the resultant field at that point C. And again the points we are taking inside the conductor, so the resultant field at this point C must be equal to 0. Then from that you will get another relation, that means Q3 expression you can write here. For example, if you want, I can write here, but you can say directly also. Directly also you can say that charges appearing on these two must be equal and opposite always. And similarly these two must be equal and opposite always. These two must be equal and opposite always. And so that if you want to prove, you can write for one plate I am proving here, for the remaining plates you can conclude that. So consider a point C in the second plate. So right, I am writing again the field at that point C here. So again I am taking this 1 by 2a epsilon naught same. Now just identify the direction. So now the direction of the electric field due to this Q1, Q2 and Q3. All these three will be towards right, and these remaining charges will be towards left. So that we need to take the negative sign. So for these three we need to take the positive sign. So I am taking this as Q1 plus Q2 plus Q3. So remaining all negative. Minus Q4 minus Q5 minus Q6 minus Q7 minus Q8. So this value will be equal to 0. So right, now we can write this expression as I am directly substituting those values here. So that implies I can write this is Q1 plus Q3 minus Q4. This Q4 I can write this as this means minus of I am writing here. This I can write this as Q2 minus Q3 plus these two values we can write it as Q3 plus Q4. This is equal to 0, right? Just again we are using these relations here. So Q4 I am eliminating there. This Q4 I can write as Q2 minus Q3, right? And so therefore I can write this as, so from this let us write this Q3 value here. So Q3 is equal to, so then I can write this as minus of Q1 minus Q2 minus Q3 minus Q4 by 2, right? If I write Q3, that means actually here 2Q3 will get, and all these are negative signs. So that I am writing that side, then you will get positive signs, and then minus Q3 we need to write, and from this I am taking this negative sign common here. Now you can observe that, now finally here what we are concluding is, so therefore Q3 is equal to minus of Q2 we can write here. So this is our Q2 expression and this is Q3 expression. Now we can observe this. Q3 and Q2 are equal and opposite. So from that you can conclude the charges appearing on the opposite surfaces will be equal and opposite. So right. So that is the final conclusion about the charge distribution here. So write that conclusions again. So again the first point also I am repeating. So both the points will be together. In parallel plate combinations, the charges appearing on the charges appearing on outermost surfaces will be equal and is equal to the half of the total charge given to the system So that is the first point. Second point, the charges appearing on opposite faces will be equal in magnitude and opposite in direction. So now let us take one example, then you will get the clarity about this standard distribution here. Just a minute. So now let us take this an example for this about the distribution of these charges here. So I am taking now 3 plates like this. Now here the charge given is 2q and this is minus q and here plus q, or I am taking here, or plus 3q, let us consider here, right? And so now that is the charge given to the different plates then. Now we need to find the charges appearing on this each surface. So now just we need to apply our basic points here, the fundamental points what we discussed. Those 2 points are the fundamental points and you need to remember those 2 points regarding the charge distribution of these parallel plates, right? So the first, let us take the distributions here. This I am taking as q1, q2, q3, q4, q5 and q6. So now previously what we discussed is the charges appearing on the outermost surfaces q1 and q6 will be same. So then q1 is equal to q6 and this value is equal to half of the total charge given to the system. So total charge given to the system is q minus q plus 3q by 2, right? So then this value will be 5 minus 4, that means 2q you will get. So charge present on the outermost surface will be 2q. And so I will write this final charge distribution here. So 2q will be there here and 2q will be there here. So that is the charge distribution, final charge. Now if 2q charge is there, always the sum of charges q1 plus q2 must be equal to 2q. So but here what we can write is q1 plus q2 must be equal to 2q. And therefore this q2 is equal to 2q minus q1, that q1 is 0. And so that means, so directly you can say that always these two charge, sum of these two charge must be equal to total charge given to the system if no other connections are there. And so that then already 2q is appearing here, so charge appearing on this will be 0, right? Now let us come to this plate here. So the total charge is, it means total charge given to the plate is 3q. Out of that 2q is appearing here, and so then remaining q will be there here. So directly I am writing here, right? And so now again we mentioned that charges appearing on these two faces must be equal and opposite, right? So then here it will be minus q, you can write here, directly you can write that. And next here, the charges appearing on these two surfaces must be equal and opposite. Here this side is 0 means this side also 0 will be there. Now you can verify that the net charge on this plate is minus q. So that is the net charge on this plate here. So those are the charges appearing on the different places there. So like that you can find the charge distributions present on these different plates there, right? And now let us take some extensions for these problems. So here mention that when one of the plate is connected to the ground. So I am taking this combination like this. Suppose here this no charge is present here, that means, or let us take some charge Q is present here and this minus Q will be presenting on this, right? So now I am taking the situation like this and I am taking this, this plate is connected to the ground here, or that is connected to the ground through the switch S, right? This is a switch S. So now write the next example. In the system shown in figure, three identical plates are placed parallel to each other and are given charges as shown. And are given charges 2Q, Q and minus Q as shown. Find the charge flowing through the switch S when it is closed. Find charge flowing through the switch S when it is closed. And so here you need to remember that again one of the fundamental point is whenever plates are connected to the ground, out of this combination you may connect any one of the plate connected to the ground. The charge appearing on this outermost surfaces will be equal to 0. So it is another fundamental point you need to remember here. Whenever, write that point, whenever any one of the plate is grounded, then the charges appearing on the outermost surfaces, will be equal to 0. Because for this we discussed already, like when you are taking a concentric shells, if this outer surface is connected to the ground here, outer shell is connected to the ground. So that means now here if suppose initially some charge Q is there here, for example, let us say Q1 and Q2 charges were given to this. Then what is the charge on the outermost surface of this shell here? Now once it is connected ground, you can verify that the charge appearing here will be 0 and here you will get minus Q1. You can verify that, we already solved that. When inner shell is grounded, what will happen, and when outer shell is grounded, what will happen. So when outer shell is connected, the charge appearing on the outermost surface will be 0. And in case of this parallel plate, that point will be true for any surface here. That means any plate, if you are connecting it to the ground, the charge appearing on the outermost surface will be equal to 0. Then only that the potential difference or the potential of that particular plate will become 0 there. So mention that point. So then when any one of the plate is grounded, the charges appearing on the outermost surface will be 0. And so that means here this side charge will be 0 and this side charge will be 0, right? So no charge will be presenting on the outermost surface. I am saying, what I am saying is, not only this plate, you may connect any plate in that combination. Automatically you will get this the charges on the outermost surface. That means charges on this surface is 0, and we already mentioned that always charge on these two surfaces must be same. And so automatically the charge on these two surfaces will be same here. And to find the charge flowing through the switch, so let us write the initial distribution and final distribution. The difference we can write as charge flowing through the switch. So whenever such a switch problems are there, you need to remember, let us write before opening the switch, or that means before closing the switch, what is the charge distribution, and after closing the switch, what is the charge distribution. That we need to write here actually. And so that means I am writing this initial. So initial charge distribution I am writing here. You know that the total charge is Q. That means total charge is 2Q net charge. And so Q by 2 means, so here it is Q and here it is Q. The initial charge. Right? That means half of the total charge given to the system. And so now here Q will be there, then here minus Q will be there. And here it is minus 2Q will be there, because sum of these two charges must be equal to minus Q. So here minus 2Q plus Q, then minus Q will get. Here it is minus 2Q means here plus 2Q will be there. Now we can verify that again the sum of these two must be equal to total charge given to the system. So this is the initial charge distribution. Directly I am writing here, right? And next, once it is closed, once the switch is closed here, then what I am saying is charges appearing on this outermost surfaces will be 0. So this is the final charge. Final charges I am writing here. And so now here it is 0 means the total charge must be present here only, right? So that it is 2q, because the sum of these two charges must be equal to 2q again, because it is not connected anywhere. And next here, if it is minus 2q, then minus 2q must be present here. Always these two will be carries equal and opposite charge. And next, here if it is minus 2q, then verify here, the charge must be equal to 3q. Because again the sum of these two charges must be equal to q, right? And so then it is a total, if it is minus 2q means plus 3q will be there. And if it is plus 3q, then here the charge must be equal to minus 3q. Because again these two charges must be equal and opposite. And outermost surface we mentioned already, that is 0, right? And so now let us identify the charge flowing through the switch here. So charge flowing through the switch is charge flowing through the switch, we can write it as, let us identify this loss plate here. What is the initial charge? The initial charge is minus q and the final charge is minus 3q. And so that charge flowing is, we can say minus 2q is flowing from ground to that plate here. So therefore this delta q is equal to q initial minus q final, we can write here the difference. And so I can write this as minus q and minus of minus 3q. And so it is 2q charge is flowing here. 2q, you can say 2q charge is flowing from plate to the ground. If they ask him particularly from ground to plate or plate to ground, we need to write the sign as I said previously. Otherwise magnitude of charge we can write here. So if they are asking like what is the charge flowing from ground to plate? From ground to plate, minus 2k is flowing. From plate to ground, plus 2k is flowing here. This is flowing from plate to ground. So like that we can find this charge flowing through the switches here. So here in this problem, the fundamental point you need to remember is, whenever a plate is connected, whenever any one of the plate is connected in this combination, connected to the ground, the charges appearing on the outermost surfaces will be equal to 0. So that is the fundamental point you need to remember here. And let us see another example based on this. Like when two plates are connected together. When two plates are connected together here. Right? And for example, I am taking the separation like this is, let us take this as this separation as 2D. Let us take in terms of A and B, then you will get a general formula for this. Let us take it as 2D and D. This separation is D. Now suppose these two plates are connected by using a switch like this, right? And so now here I can take this as 2q minus q and this is 2q, right? Let us take it as 3q for example, because those two are connected together. Now these are the three plates here. The plates A, B, C, let us name here. This is A, B, C. So three plates are given the charges like that. Now we need to find when the switch is closed, then what is the charge flowing to the switch we need to find here. So write that problem. In the system shown in figure, so directly about all the information is there in that figure. In the system shown in figure, the switch SC is initially kept to open. Then find the charge flowing through it when it is closed. Right? And so now here again let us write whenever switch problems are there, as I said, we need to write initial charge distribution and final charge distribution. So then initial charge distribution and the initial charge distribution. So then total charge given to the system, that means 2q minus q, that means q plus 3q, 4q by 2, 2q. So this side 2q will be there, and so this side 0, and so this side 0 minus q, and then here it should be plus q, and this side should be 2q. Now anywhere you can observe that conservation of charge is valid. So 0 plus 2q, 2q, 0 minus q, and q plus 2q, 3q. So that verifies automatically there, right? And next, so now when these two are connected together, right? So the charges appearing on the outermost surfaces, the charges appearing on the outermost surfaces will be half of the total charge given to the system. So that means final I am writing here. So final charges. So this will be 2q and this is 2q. Since it is not grounded, the charges will, final charges will remain same, or if you want you can verify that, right? Now here I am taking it as some q1. Now this charge need not be 0 here, because some charge may flow from this side, because these two charges now need not be equal to 2q, because some charge is flowing through this conducting wire, right? And so now if it is minus q, then it will be, it is q means then here minus q1 will be there. And so then here similarly, if it is 2q is there, then I can take this side as some charge q2, then this side minus q2 will be there, right? I am taking the charge distribution like that. Now here what we can write is, we can apply now conservation of charge on these two plates. Sum of charges on A and C remains same, because those two plates are connected together. So that means now initial charge will be 2q plus 3q, that is initial sum of charges here. Now final charges are 2q plus q1 plus 2q plus q2. Means this is the charge present on this plate, first plate, and this is the charge present on the second plate. And so now this we can write it as, that means 5, and this side 4q will get, q is equal to q1 plus q2 we can write. And actually in this problem, as the 3 plates are there, this relation you can also get by writing the charges on these plates here. Here also you can verify that minus q1 minus q2 is equal to minus q. So minus sign will be cancelled. So q1 plus q2 is equal to q. So that is one relation what we can write here. And next here we need to write this, whenever such a connections are there, we need to write the potential difference. So if once capacitors are completed, we can write potential difference by the definition of the capacitor we can calculate. And now here we write, as the capacitance is not completed, we write the potential difference in terms of this field. So we know in between these two plates uniform electric field will be there, right? So then due to this sigma by epsilon 2 epsilon naught, and due to this sigma by 2 epsilon naught, both are in the same direction, because one carries a positive charge and other carries a negative charge in between these two plates. And then that resultant field into, that means the field into the distance we need to write, potential difference means, because that is a uniform field. So now here just I am doing this calculation here, because actually the field at this point, suppose if I want to write here, that E is equal to E1 plus E2. Now E1 is Q1 by 2A epsilon naught plus Q1 by 2A epsilon naught, right? Because electric field due to this will be along this direction E1, and electric field due to this charge will be along this direction. And electric field due to all remaining charges will be cancelled. You can verify that. Electric field is due to this Q2 and this Q2 will be cancelled, and electric field due to this Q2 and minus Q2 will be cancelled, plus Q2 will be cancelled. You can verify that. So only in this region, these two charges only will produce that field. So that is nothing but what we are writing here. And so I can write this as Q1 by A epsilon naught we can write. And so now the potential difference we need to write here. Just that potential difference formula I am writing here. The potential difference we can write as E into the distance between them we can write here, because that field is a uniform field. So now that means now in such a problems we need to write that potential difference, we need to write like this. That means when we need to write the potential difference in case of this parallel plate problems means whenever such a connections are there, whenever any plates are connected in the group, then we can use the potential difference relation here. So how to use that potential difference relation means, suppose say this is, its potential is VA, and its potential is VB and its potential is VC. So what we can write is VA is equal to VC, right? Because these two are connected together. And so charge will flow from one plate to another plate until they get the common potential, right? And so that these two are equipotential. Let us take for example 20 volts, both are at 20 volts here, and this is say 5 volts. Then 20 minus 5 is 15 volts you will get. And similarly here 20 minus 5 is 15 volts you will get. So potential difference between these two plates and these two plates will be same because these two are at same potential. That is nothing but what I am writing here. That means after writing this relation, we need to use the potential difference relation. So now potential difference between A and B is same as that of potential difference between C and B. And here this order is also important here. So that means if you are this side if you are writing A and C, and this side you need to take C and B only, right? And so now here this value I can write as E1 into 2D, where E1 is electric field, that means, or let it be E electric field in that direction, and similarly you can write this electric field in this direction as E2 dash or E dash along this direction. I am taking just it as E dash. So then E dash into D along this direction. Then this E is nothing but Q1 by A epsilon naught into D, 2D. This is equal to Q2 by A epsilon naught into D. Right? So I can write this relation as Q1 is equal to Q2 is equal to 2Q1 we can write here, this relation, right? That means sigma by epsilon naught into whatever the distance between those two plates is there, that distance we need to write here, right? And so now, this is another relation here. From equation 1, what we can write is, from equation 1, Q1 plus 2Q1 is equal to Q. That means instead of this Q2 also I am substituting this value here, 2Q1. Therefore, this Q1 is equal to Q by 3 we can write. And so therefore, what I can write is, this is Q1 value, therefore Q2 value we can mention it as 2Q by 3. And so now let us write our question is, that means that is the charge distribution. Now we can write the charge flowing through the switch. So now let us see how to write the charge flowing through the switch. Charge flowing through the switch. So charge flowing through the switch we can write it as QA initial minus QA final. This model you can consider here, and that side also magnitude you will get here, magnitude of charge I am writing here. That means I am taking A, you may consider C also. That means whatever the initial charge present on A minus final charge present on A, or you may write initial charge present on C or final charge present on C, because charge distribution is taking place between them. And so this is mod of 2Q minus the final charge, means these two charges we need to add here. So the final charge is nothing but 2Q plus Q by 3. So it is 2Q minus, so it means finally we will get this Q by 3 here, or minus Q by 3, mod of minus Q by 3. So just I am writing magnitude, that's what I am saying here. So Q by 3 is a charge flowing through the switch here. So Q by 3 charge is flowing from the switch here, or that means Q by 3 is charge increasing on this actually. So that Q by 3 is charge is flowing from C to A you can answer, or minus Q by 3 is flowing from A to C you can answer there. So like that, if they are asking particularly direction, then you need to write the sign also. Just if they are asking the sign, then no, just if they are asking the charge flowing through the switch, no need of writing the sign, just magnitude is sufficient there. So like that we can find the charge flowing through the switches there, whenever such a combination of charges are there. So regarding the fundamental, regarding these parallel plates, you need to remember some fundamental points. The first point is charge present on the outermost surfaces, charge whatever may be the number of plates. So charge present on the outermost surfaces will be always equal, and if no other connections are there, then that charge will be equal to half of the no other charges, means no grounding is not there, then charge present on the outermost surfaces will be equal to half of the charge given to the system. And the second fundamental point is the charges appearing on opposite surfaces will be equal and opposite always, whether connections are there or connections are not there, this point is always valid. And next point, if any one of the plate is grounded, then charges appearing on the outermost surfaces will be zero, both the surfaces will be zero, right? And then next term, if any such a connections are there, then we need to use this potential difference relation here. The potential difference between these two plates and potential difference between those two plates will be equal. And here again I am saying this order is important. The order in the sense, for example, according to our assumption here, for example, -2q minus q2 we are taking here according to some assumption. Then here you need to take that sign only we need to consider here. That means here if you are writing VA and whatever the charge is there, that charge we need to write along with the sign. And similarly, if you are taking here Q2, and that means what, if you are taking charge on A here in this expression, then here we need to take charge on C only along with the sign. So that is important here. This order is important here. That means you can't equate like VA minus VB is equal to VB minus VC. That relation will be wrong relation there. So that also you should take care here about this. That is that means about the parallel plate problems there. And again we will discuss some more problems based on this when we are discussing about this capacitors, right? Because actually this arrangement is nothing but we can call it as one capacitor here, these two surfaces together. That we will discuss in capacitors there. Thank you.